This is Precalculus video lecture number 15 on properties of rational functions. So first, our definition: a rational function is a function of the form f of x equals g of x over h of x, where g of x and h of x are polynomials and h of x does not equal 0. So it should remind you of our definition of a rational number. Rational means there's a ratio, right, of two quantities, and in this case, the two quantities are polynomials, which we just studied in the previous lesson. So anytime you have a rational function, it's because you have a ratio or what looks like a fraction involving two polynomials. And just keep in mind here that h of x or whatever's in the denominator cannot be 0. So remember, the domain of a rational function is going to be all real numbers except whatever would make the denominator 0. We have to exclude those from the domain. So first we're going to practice identifying the domain for different rational functions. And we're kicking it off with example 1a, f of x equals x over x minus 6 times 2 minus x. So pay no heed to the numerator. When you're trying to figure out the domain, just look at the denominator. Remember, we don't want the denominator to be 0, which means x cannot be positive 6 and x cannot be 2. Okay, so you've got two ways you could write this domain out. Probably the easiest is using set builder notation. So in that case, you would say the domain, put D, is the set of all x's such that, that's how you read the vertical line. You say such that x does not equal 6 or 2. And it's implied or understood that all other values of x are okay. They're allowed in the domain. Just whatever you list with the not equal to sign, those are the restrictions that you have to take out. Other option is if you want to write it in interval notation. Probably not as easy because it's a little trickier to exclude values, right? So think about it. If you graph it, you want everything on the real number line except for 2 and 6. So what would that look like? Well, you would have everything part of the domain, but not 2, everything in the middle here, not 6, and then everything onward and upward to positive infinity. So in interval notation, the domain would be from negative infinity to 2 with parentheses because we're not including 2. And then you go union from 2 to 6. So that's how you skip over 2. You can't cut it off at like 1.9 because what about 1.99 or 1.999? That's part of the domain. And then same thing on the other side. You can't cut it off at 2.1, 2.01, 2.001. So you just include 2 with parentheses. So the restriction's not there. And then union 6 to infinity. Okay, the directions didn't specify which way to write the domain, so it's up to you. I think for this problem, those set builders a little cleaner. What do you say? Okay, next example. We have x minus 1 over x squared plus 3. I noticed just like in the last problem, I didn't pay any attention to poor little x in the numerator. Oh, yeah, the numerator doesn't have an impact on the domain. When we're trying to figure out the restrictions, you just need to look at the denominator. Okay, so in this case, I'm going to focus in on the denominator, x squared plus 3. And just remember, okay, what would be a problem here? Well, a problem would be is if x squared plus 3 is 0. I don't want that to happen. So x squared plus 3 cannot be 0, which means x squared cannot equal negative 3. But is it possible? Can you think of any real number if I were to square it that it would come out to be negative 3? No way, that's never going to happen. So what does that mean for us? That means that there's no restrictions. I don't have to worry about the denominator being 0, ever. It's not happening. And if you look back, it should make sense. You have x squared plus 3. So if you take a number and you square it, it's not going to be negative. Worst case scenario, it's 0. And then I'm adding 3 to that. So there's absolutely no way we're going to have a 0 in the denominator. Even if you think, oh, I'm going to get wild. I'm going to plug in negative 1 million for x. If you square it, it's positive. Now you're adding 3, still not 0. Okay, so cool. That means there's no restrictions. So how do we write up our domain? Well, our domain would be all real numbers. So, I mean, you've probably seen it. You could write x such that x is any real number. I mean y, that's just too much writing. So usually I'll opt for using the all real number symbol, or if you're going to write it in interval notation, then it's from -infinity to infinity. All right, beautiful. Let's move on. Example C. F of x equals -2 times x squared minus 1 over x squared plus 2x plus 1. Oh, how mean. This time they didn't factor the denominator for us, so we got to go ahead and factor that. That's a perfect square trinomial. Did you notice? That's the quantity x plus 1 squared. And remember, I don't want that to equal 0, which means x cannot equal -1. So that's my only restriction. So the domain is going to be the set of all x's such that x does not equal -1, and it's understood that everything else is okay. Or if you want to use interval notation, then you would say -infinity to -1 union -1 to infinity. All right, how we doing? Okay, now we're going to talk about vertical and horizontal asymptotes for rational functions. You should be familiar with the idea of vertical and horizontal asymptotes at least a little bit from trigonometry. Remember, certain functions like tangent of x, cotangent of x, secant of x, cosecant of x, they have vertical asymptotes, and other trig functions like tan inverse of x has a horizontal asymptote. So this shouldn't be the first time you've heard of such a thing. Anyways, it's basically a line. It's not part of the graph, but the function approaches it. Okay, vertical asymptotes are never crossed. Horizontal asymptotes are occasionally crossed. So we'll talk about the difference. The vertical asymptotes of a rational function can be found by setting the denominator equal to 0 and solving for x. This is only true after f of x has been completely simplified. We'll also discuss what that means in a second, but I just want you to take note of that. So yes, you look at the denominator to figure out where the vertical asymptotes are, but only after you've simplified your function. Okay, vertical asymptotes are never crossed, because basically they come from where the denominator is 0. So they come from specifically the values of x that are excluded from the domain. So there's no way, no how that the function is going to cross them. Not always the case with the horizontal asymptote. Horizontal asymptote, the main thing to remember, especially when you get to calculus, these tell you about the end behavior. And remember, we've talked about end behavior a little bit before when we were looking at power functions in the previous lesson. Basically, like if you zoom out, what is the function doing in the long term? So the horizontal asymptote tells you when x gets really big or when x gets really small, the function's approaching some value, but it doesn't mean it might not be crazy in the short term in a small window and maybe cross it here and there. Okay, and once we look at some examples, that'll make more sense. But just think horizontal asymptotes have to do with end behavior, and sometimes the graph can cross, and I'll show you how we check, okay? So horizontal asymptotes don't come because of a domain restriction. It just tells you end behavior. You can cross them. Maybe you have a rebel function in the short term. Vertical asymptotes, never going to happen. Okay, so here we're going to dissect this definition. Don't let it get confusing, okay? You can handle it. We have a polynomial. Here's our function, okay? We have a polynomial in the numerator and a polynomial in the denominator. And they're telling us the leading terms are not 0. Okay, fantastic. First thing, if n is less than k. So n would be the degree of the numerator. K is the degree of the denominator. So the first thing is if n is less than k, meaning the denominator has a higher degree than the numerator, then automatically the x-axis or the line y equals 0 is the horizontal asymptote. Do you want an example? Say f of x is x squared plus 1 over x cubed. You see how the denominator has a higher degree than the numerator? then that means y equals 0 is the horizontal asymptote. Okay, second case. If n is equal to k, meaning the degree of the numerator is the same as the degree of the denominator, then the line y equals an divided by bk, that's the ratio of the leading coefficients. So an, you would take the coefficient from the leading term in the numerator, divide it by the coefficient of the leading term in the denominator. That's going to give you the equation for the horizontal asymptote. I'll show you how. Last case. If the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. Okay, and we'll talk about what happens with the n behavior. If n is bigger than k by exactly 1, then there is an oblique or slant asymptote. That's what OA stands for, oblique asymptote. And that's only if the difference is exactly 1 between the degree of the numerator and denominator. There's also parabolic asymptotes if the degree difference is 2, but you're not responsible for having to graph any of those, so don't stress, but know they exist. And we'll talk more about that later. I don't want to overwhelm you guys too much. Okay, also, to find the equation of the oblique asymptote, you have to do polynomial long division. If you forgot how to do it, I will link a video right here in the upper corner explaining how to do polynomial long division. You can't do synthetic division to find the equation of oblique asymptotes. I'm sorry. It won't always work out properly. All right, so here we go. Let's look at some examples, and then once we work through them, I think you'll feel a lot better about what's going on and how to sort through it, okay? Good. So here's what we need to do. Find the vertical, horizontal, and oblique asymptotes, if any, of each rational function. Now, I just want to be clear. We're going to find vertical, and then if there's horizontal, then there's not going to be obliques. You won't have both. So it's one or the other, or it could be neither. Okay? Very good. So let's look at f of x, this first function here. F of x is equal to 2x plus 7, and I'm going to factor the denominator. So it's x minus 2 times x minus 1. Okay, is this guy completely simplified? Why, yes, it is. So let's see, where's the vertical asymptotes? Remember, they come from where the denominator would equal 0. They're exactly the same thing as your domain restrictions for this case. So the vertical asymptotes would be at x equals 2 and at x equals 1. Now what about the horizontal asymptotes? Okay, well, we have to figure out what case we're in. So let's look here. What degree is the numerator? What's the highest power of x that you see? The degree is 1. And then what about the degree of the denominator? It's 2. So we're in the first case. Anytime the degree of the denominator is bigger, if it's bottom heavy, then automatically your horizontal asymptote is at y equals 0. That's it. Okay, and we're done. We're not graphing today. That comes later. Okay, next example. F of x equals 5x squared plus 3x minus 1 over 4x plus 1. Okay, so let's see here. Can I simplify or factor the numerator at all? It doesn't look like it, right? So f of x is 5x squared plus 3x minus 1. Nope, that won't factor. Over 4x plus 1. So here we go. Let's find the vertical asymptotes. Looks like there's only going to be one. It's wherever the denominator would equal 0. So that would be at x equals negative 1/4. Okay, what about horizontal? Well, what's the degree of the numerator? The degree of the numerator is 2, right? Since we have x squared. And the degree of the denominator is 1. So if the degree of the numerator is bigger than the degree of the denominator, then there's no horizontal asymptote. Oh goodness. However, I do have an oblique or slant asymptote. You'll see both terms used depending on the book, so I'll just use them both. That way you're equally familiar. We do have an oblique asymptote because these are 1 degree apart. Okay, so to find the equation, we need to long divide. And here we go. So I have 4x plus 1. I'm going to divide that into 5x squared plus 3x minus 1. Okay, so when you long divide, remember, you just pay attention to the leading term. So 5x squared divided by 4x, that's going to be, well, maybe you are confused, 5x squared divided by 4x, that's just going to be 5/4 x. So that goes up top here. Then I multiply that by 4x plus 1, so I'll get 5x squared plus 5/4 x. Then we subtract. This cancels out. Then I have 3x minus 5/4 x. Okay, so 3x is 12x. 12x over 4 minus 5/4 x. So this is 7/4 x. And then bring down the minus 1. And then I have to repeat the process. So let's see here. 7/4 x divided by 4x. That's 7/16. So that's going to go up top here. And then we have 7/4 x plus 7/16. Now I subtract. This cancels out. -1 is -16/16 minus 7/16. This is -23/16. So this is my remainder down here, hanging out. That's the remainder. Okay, and when you write the equation for the oblique asymptote, you ignore the remainder. Oh my goodness, why? Let me show you. So the equation of the oblique or slant asymptote is sitting right up here. It's your quotient. So it's equal to, we're going to write it as y equals 5/4 x plus 7/16. Okay, plus you have this remainder, -23/16 over 4x plus 1. You're going to ignore the remainder. Don't include it anytime you write the equation of the asymptote. Why? Well, later on when you get to calculus, you're going to learn these asymptotes tell you about end behavior, right? End behavior when x gets really, really large. And if you'll notice, this asymptote is always just going to go to 0 if x gets really, really large, because the denominator is going to get so big that that term's just going to shrink and become insignificant. But I'll let your calculus teacher explain all that good stuff to you. Just know you don't need the remainder when you write the equation of the oblique asymptote. There it is. It's a line, right? Slope is 5/4, y-intercept is 7/16. Cute, cute. Okay. Moving on. Are you ready? Example C. We have f of x equals 6x squared minus 4x plus 3 over 2x squared plus x minus 1. Okay, we got to factor this bad boy. Does the numerator factor? Let's see. Can I think of two numbers that multiply to 18 and add up to -4? No, I don't think so. So nothing is going to reduce. So we'll just leave it. 6x squared minus 4x plus 3. And then 2x squared plus x minus 1. Let's see here. So 2x, x. It has to be a 1 and a 1. And if I want positive x in the middle term, there we go. Okay. So vertical asymptotes would be at the zeros of the denominator. X equals 1/2 and x equals -1. Horizontal asymptotes. Well, what's the degree of the numerator? The degree of the numerator is 2, right? Since we have x squared. And the degree of the denominator is also 2. Oh, wow, wow, wow. So this is that case we haven't considered yet, if the degree is equal. And what you do is you take the coefficients of the leading term. So the leading term in the numerator is 6x squared, so I'm going to take 6. And then I'm going to divide it by the coefficient of the leading term in the denominator, which is 2. So I get 3. So my horizontal asymptote is at y equals 3. Very nice. Now I did want to mention something because we talked about the function needing to be in lowest terms. Okay, so here we go. I'm making up a new one. So say f of x was equal to x squared plus x minus 12 over x squared minus 9. And I'm going to ask you to do the same thing. Find the equation of all of the asymptotes. Well, we would have to factor. So here we would have in the numerator x plus 4 times x minus 3. And then in the denominator, we have x plus 3 and x minus 3. So notice this function is not in lowest terms. It can be reduced. I can cancel out the factor of x minus 3. And then from here, we can decide where the vertical and horizontal asymptotes are. Okay, so vertical asymptote would be at x equals -3 only. And horizontal, you could use the original or the reduced one. It doesn't matter. The degree of the numerator is 1. The degree of the denominator is 1. Or if you looked up before you canceled, degree is 2, degree is 2. Either way, they have the same degree. So you're going to divide the coefficients of the leading terms, which is 1 divided by 1. Same thing here if you did it with the reduced form. So y equals 1. Okay, do you see that? So x equals +3 is not a vertical asymptote. However, I do want to emphasize, what is the domain for f of x? What values of x are we allowed to plug in and which ones are we not? Look at the original when you're deciding the domain, right? That's how original f of x was handed to you before you tampered with it. That's right, we have two restrictions. X cannot equal plus or minus 3. However, only -3 is a vertical asymptote. Since x minus 3 canceled out, that means something else is going on in the graph, and we'll study that later. But basically, you have a hole at x equals 3. And when you get to calculus, you'll learn that's a removable discontinuity. But for our purposes, think of it this way. If you have a factor that's a 0 in the denominator, but it cancels out, it's less dangerous. So it's not a vertical asymptote. It gets demoted to just being like a little hole that gets plucked out of the graph. And we'll graph some of those in the next lesson so you can see exactly what I mean. But just be careful when you're finding vertical asymptotes that you make sure your function is in lowest terms, that you factor and reduce. That's the biggest thing to remember from this example. All right, cool. Now we're going to graph rational functions just using transformations. So we're going to take our parent functions f of x equals 1 over x and 1 over x squared, and then graph them according to transformations here. So if you need to revisit transformations or graphing what the parent functions are, I'll link the videos right here. So f of x equals 3 plus 1 over x squared. So the parent function that we're working with is y equals 1 over x squared. If you'll remember, the key points were -1, 1, 1, 1. We had asymptotes at y equals 0 and x equals 0. Do you guys remember what the shape was? It's like this kind of a thing. Okay. So let's see what transformations are going on here. All that I notice is this +3. So we're going to take the graph and shift it up 3 units. Okay, so in order to change my key points, I'm just going to add 3 to the y coordinates. So I have -1, 4 now. X doesn't change. And 1, 4. Beautiful. What about the asymptotes? Do they move? Well, I added 3 to the y coordinates, so my horizontal asymptote at y equals 0 is going to move. Add 3 to that. The vertical asymptote, I mean, it moves, but you won't be able to tell. It's still at x equals 0, right? If it's a vertical asymptote and you move it up 3 units, how would you ever know it moved? You wouldn't. That's the answer to that. Okay, so let's graph everything, putting it together. Put your asymptotes in there. For x equals 0, I'm going to just show a little bit beyond the y-axis so we don't forget it's there. And then y equals 3 is right here. Fabulous. And then we have negative 1, 4, 1, 4. And here's our graph. Don't forget the arrows. Don't cross those asymptotes. Beautiful. All right, moving on. Example B, f of x equals 2 over x plus 3 squared. If it's easier, I kind of want you to think of this as 2 times 1 over x plus 3 squared, if it's going to help you recognize the transformations. Because notice this is a stretch by 2, and then this takes the graph, shifts it left 3 units. So I'm going to list that out right now. We're going to stretch by 2, and then shift left 3. Same parent function, so same key points. So we have negative 1, 1, 1, 1. If I stretch by 2, I'm going to multiply y by 2. And I can do the shifting at the same time because it's affecting the x coordinate. So since they're affecting different coordinates, we're fine. And then I'm going to subtract 3 from x. So let's see. New x coordinates, if I subtract 3, are going to be negative 4 and negative 2. And then if I multiply y by 2, they're both going to be 2. 2, 2. Okay. Looks good. And then our asymptotes, what happens to them? So remember, they start off at x equals 0 and y equals 0. If you stretch, if you multiply y equals 0 or x equals 0 by something, nothing's going to happen. The asymptotes only change if you shift vertically or horizontally. So in this case, since we shifted to the left, the horizontal asymptote won't move, but the vertical one will. It'll be at x equals negative 3. Okay, and if you're having a hard time with that, just think you do the same thing to the asymptotes that you did to the points. So like if I subtracted 3 from these coordinates, you're going to take the original asymptote. Original was x equals 0. We subtracted 3 from x. We'll subtract 3 from that x also. And then you see how here we multiplied y by 2 for the new key points. Well, originally it's at y equals 0. If you multiply 0 by 2, it's still 0. So you could treat the asymptotes, finding the new ones, similar to how you get the new key points, if it's easier for you to think of it that way. All right, so let's graph this. We have y equals 0, so that's the x-axis. X equals negative 3. That's right here. And then we have negative 4, 2, and negative 2, 2. And here we go. Don't forget, x-axis is your horizontal asymptote. Good, good. Arrows on the endpoints. Love it. Okay, last one. F of x equals x minus 4 divided by x. Now, this one might be tricky to recognize what transformations are going on. So here's how I want you to rewrite it before you get going. You're going to rewrite this as x divided by x minus 4 divided by x. Oh yeah, so then that's 1 minus 4 divided by x. And maybe you're still not loving it. So here, one more rewrite. Negative 4 over x plus 1. Now if you look at this thing, could you tell me what the transformations are? I hope so. So the parent function is 1 over x, right? Y equals 1 over x. So the key points are negative 1, and 1, 1. Okay, what transformations are going on? I see 3. Do you? I see a negative. I see a 4. Normally that's a 1. And then I see a plus 1. So what are the transformations? Well, you have to reflect and stretch first. So we reflect over the x-axis. If you had left the negative in the denominator or outside and you thought it was a reflection over the y-axis, that's fine. Believe it or not, it would work out in the end as long as everything else was done properly. Okay, 2. You're going to stretch by 4. And then lastly, you're going to shift up 1. You have to do that last. Otherwise, it would get messed up. Okay. All right. So here we go. To take care of, I can knock out the reflection and the stretching at the same time, right? If I just multiply the y coordinate by -4. So let's do it. So efficient of us. So x stays -1 and 1. And then my new y coordinates, if I multiply them by -4, are going to be +4 and -4. And then last thing I need to do is shift up 1. So x's aren't changing. And then if I shift up 1, I'm going to have +5 and -3. Woo, okay, so those are our final key points. And then let's think about the asymptotes. So the asymptotes start at y equals 0, x equals 0. If I multiply y by -4, that's not going to do anything. But here, oh, I forgot to write it. You add 1 to y. Add 1 to y. So that's going to move the horizontal asymptote up to y equals 1. Add 1 to it. X equals 0 stays the same. All right, good. Now let's put it all together. So we've got x equals 0, there's our vertical asymptote. Y equals 1, there's the horizontal asymptote. And then we have -1, 5, 1, -3. Don't forget 1 over x has a different shape than 1 over x squared, right? The pieces of the graph are on opposite ends. And there we go. You know, I feel a little ill. Let me put the proper x-intercept in, right? You could tell if x is 4, we have an x-intercept. And this is just training from my youth. If I cross an axis, it should be correctly shown, right? Okay, I was gonna lose sleep if that was in the wrong spot. Hope you enjoyed the lesson. The next one is going to cover graphing rational functions and all of the steps that we need to cover. Similar to the previous lesson, how we graphed polynomial functions and all the different steps. So stay tuned, that's gonna be an exciting one. And then we're gonna be wrapping up this unit pretty soon. Don't forget to give this video a thumbs up, subscribe if you haven't already, share it with your classmates and your friends. I'd really appreciate it, and have a great day.